in the last bit, we're going to look at, just because it's important to know that it exists, is that we can react our aromatic rings with a nucleophile. So we've done electrophile so far, but we can do a reaction with a nucleophile. But what we're going to see is that it requires some very specific conditions for it to happen. Okay, so it requires a very specific set of factors. So where we've done the ring acting as a nucleophile, now we're going to look at the ring acting as an electrophile. So that actually helps us to understand that we want the ring to be an electrophile. So what conditions do we need? Well, the first thing we need is we need it to have a very good leaving group. Okay, so we need there to be a leaving group present. So the examples we gave before were using just benzene. It was just the ring by itself. But what we're saying to have nucleophilic aromatic substitution, we need the ring to already be substituted. And we need it to be substituted with something which can act as a leaving group. And then the other thing we need it to have is it's got to have what's called an electron sink. So this is an electron withdrawing group. We're going to look at this in a much more detail in one will it be tomorrow. Okay, but an electron withdrawing group is something, and we'll see an example of the nitro group as an electron withdrawing group, which actually draws electrons out of the ring. So what that's doing is it's making the ring less electron rich, which means it's going to be more susceptible for a nucleophile to attack it. So at the moment, we're saying that the ring acts as a nucleophile because it's got lots of electron density. So what we've got to do with this is find a way of removing some of the electron density from the ring. Okay, so that's what an electron withdrawing group does. And so it makes the ring less electron dense, so it makes the ring slightly electron deficient, and therefore if you have a nucleophile floating around, the nucleophile will react with it because it's electron deficient. Okay, so we've got the leaving group and we've got the electron withdrawing group. Okay, so let's have a look at why we use this particular set of factors. So we draw our ring. Okay. The leaving group, we're not going to worry too much what the leaving group is. Okay, it's just going to be any leaving group that we want, but we will put in a specific electron withdrawing group. It's the one that we've seen before, which is the nitro. Okay. So how does the nitro group withdraw electrons from the ring? Well, if we go through the mechanism, if we say, right, let's trust me for a little bit, we're going to do the mechanism and then we're going to explain what's going on. So, the nucleophile, up here again, we don't care what nucleophile it is for now, we're just going to use any generic nucleophile. This is going to attack the carbon in the ring that has the leaving group attached. And then, of course, you guys might think, but that's really straightforward now because it's just like an SN1 or SN2 reaction. You know, it's an SN2, we can just make the leaving group leave at this point. But the problem here is that isn't going to happen because when we attack that carbon, we have more than just single bonds, we have a double bond. And what we know, and we'll learn in carbonyl chemistry, is that double bond is the weaker bond. So we're not going to break the bond between the carbon and the leaving group before we break the bond between the carbon and the carbon, before we break that pi bond. So what will actually happen is we will break the bond. So it's, again, we're kind of doing the same as we did with the electrophilic addition in that we're taking electrons out of that bond to break the aromaticity. It's just the electrons are staying with the ring, but it's no longer in this aromatic system. So what happens here is we then have we have a negative charge there, and we have the nucleophile and we have the leaving group. Okay. So what happens next? Well, we can move, just like with the resonance structures we did before, we can do resonance structures here. And what's really important is to show that this negative charge can form a double bond here, which means that this carbon would have too many bonds, so it would break its bonds down to here. So this is a resonance structure. So the nitro group is still unchanged. Okay, so we've moved our group down, our negative charge down to the bottom of the ring. And then you've got a nitrogen there that's positively charged. So the nitrogen, very electronegative, or much more electronegative than the carbon. So which one would be more stable with positive charge? Well, the nitrogen doesn't really want to have its positive charge. The carbon next to it has got an abundance of electrons. So of course the nitrogen's going to say, well, I'll take those electrons so I can try and get rid of this positive charge. Okay, so the nitrogen would try and get rid of its positive charge. It will say X, and I've got some extra electrons. But of course it can't have enough. It can't have more than 4 bonds. So by forming a double bond between the carbon, it would have 5. So it needs to do something. And of course we've got the nitrogen double bonded to oxygen, so we would break the nitrogen-oxygen double bond. So the poor nitrogen still ends up with a positive charge. Okay, but the oxygens now have got 2 negative charge, and the oxygens are really happy because they're even more electronegative than nitrogen. So if an oxygen gets to have extra electrons, it will do. So this is the resonance structures. This shows that you can move that charge, that negative charge, around the ring once a nucleophile is attacked. And that's got it in a position now where we've removed that electron, those extra electrons, out of the ring system. Okay, and what we're now going to do is put it back into the ring system. So,
on the third figure, is that minus from carbons towards the bond between C and
yes,
or?
yeah. So this, I'll show it this way. This is going to form a double bond like that. Okay. Okay. So what we can now do is we can reform the aromatic ring, so we can basically do the reverse of what we've just done. We can reform that carbon-nitrogen double bond. We can break the nitrogen-carbon double bond, putting those electrons back into the ring. Again, this is all in equilibrium, this is all a resonance, it's all a movement over time. We can then form our double bond up here. Now this carbon has 4 single bonds at this point, so it can break one. And the one that it's going to break is going to be the one with the leaving group, because that's going to give the most stable result. It's going to be the leaving group that will leave. So we can do that. And the result is we've added the nucleophile to the ring. So the important thing is that this doesn't happen if you don't have that electron withdrawing group. That electron withdrawing group activates the ring for the attack by the nucleophile. And when I'm talking about, when I say the para position, we'll cover that on the next slide. The para position is the one in which the nitro group, if we said the nitro group is our substituent, we can count or assign positions on the ring relative to that nitro group. So what we're saying is it's the para position relative to the nitro. So the leaving group and the nitro group must be para to each other for this to occur. Okay. So when I say orthometric para, what I mean is once we substitute a ring, okay, there are different reactions that occur relative to the substitution pattern. So if we take X as being the substituent that we're interested in, okay, if Y, another substituent, is right next to it, we would call that ortho. If it was 1 carbon away, we would call it meta. And if it was 2 carbons away, so opposite, we would call it para. So we've got ortho, meta, and para. And you can see that on the far side, the para, where X and Y are opposite one another, that is just like the example we had with the electron withdrawing group and the leaving group opposite one another. So I said that the para was really important for this. And what about the other substituents? What if we had a position where it was ortho rather than para, or meta rather than para? Well, so this is what we had. We said the leaving group went to the nucleophile if it was in this position. So what happens in the ortho example? So let's just draw, let's draw that in. Okay, so we've got our leaving group here, and we've got our nitro group here. Okay. If you don't get the reaction mechanism down, just because I'm looking at the time, don't worry, this will be online afterwards. The key bit is going to be that we're going to show, does the ortho position work and does the meta position work? And that's the key take-home message. So if we do this reaction, we can show that we can move the electrons through the ring, or out of the ring, I should say. So we've got our nucleophile, we've got our leaving group, okay? So we can do the same thing in the ortho position. We can move the electrons out of the ring onto the nitro group, and then we can reform the ring afterwards. Okay, so we can take them out. Okay, so with the ortho position, we can do the same thing. Okay, what about with the meta position? Well, with the meta position, let's have a look. Okay, so we have our nucleophile. It comes in and attacks again, exactly the same thing. Sorry, my arrows are getting more and more. Okay. Okay, so our negative charge sits there. If we do the resonance structure, well, we form this here. We're not going to break that carbon-nitrogen single bond because we've got this carbon-carbon double bond. So we're actually going to end up with the negative charge at the bottom. Okay, so with the meta, we can't use the nitro group to stabilise the resonance. We can't take the electron density out of the ring. Okay, and that means that this is very unfavourable because it's that moving it out of the ring and then back into the ring that allows the leaving group to leave, and it gets really complicated. Why? You have to start looking at things like the orbitals that are involved and the direction of attack of electrons. So it's one of these where you kind of have to take my my word for it that, you know, the most important thing is that you have to take the electrons out of the ring first to be able to put them back in. If you really want to understand it, then we can talk about molecular orbitals and the HOMOs and LUMOs and antibonding orbitals and direction of attack of electrons into orbitals. You know, it's up to you, but trust me, all I'm expecting you to be able to tell me is, you know, the meta can't undergo this, and to show the reason why is that when you draw these resonance structures, you cannot take the resonance out of the ring onto the nitro group with the meta position. So in the meta position, you wouldn't get nucleophilic substitution.